Imagine you're a chick and you have to decide what to eat for lunch. You only have one of each item, and every food has a happy score representing how satisfied you are when you eat it, and a weight value indicating how heavy it is. You also have a maximum weight of food you can eat, and let's say that's 7 weight units. Now you want to get the maximum happy score, so how would you guarantee the best combination of food to eat? Here is where dynamic programming can help you. Dynamic programming is a mathematical optimization method, which means that it's an algorithm designed to give the optimal or best solution to a given problem. You can use it when the problem you want to solve can be divided into smaller subproblems, and then when the answer of these subproblems can be used to calculate answers to other subproblems. In this video, we'll be using a table to help us solve these subproblems. A table goes from 0 to 7, which is because the max weights below 7 are smaller problems that will be used to calculate and compare values in other rows that will eventually give our final answer. Our rows each have food items going from 1 to 5, and we'll explore different subproblems with certain food items available. For example, in the second row, we only have breadcrumbs and a berry available. In our first square, the max weight is 0, and we only have breadcrumbs available, but we can't actually pick the breadcrumbs up since they have a weight of 1, so our max happy score for this subproblem is 0. Now when the max weight is 1, we're able to pick up our breadcrumbs. Since we can only pick them up once, as the max weight increases, each max happy score is still 1. Now we include the berry in these subproblems, but we can't consider picking them up until the max weight is 3, so our optimal solutions remain the same up till that point. When the max weight is 3, we'll have to make a comparison with the answers in the previous row and make a choice. Either we pick up the berry or not. We can keep our answer to the preceding subproblem, which is 1, or we choose to pick up the berry and move back to the weight that would let us add it and ensure that it's below the max weight of the subproblem while maximizing the scores. In this case, we would move back 3 to a weight of 0 to allow us to pick up the berry, which has a weight of 3. Now let's look at the happy scores. 0 plus 4 is 4. Is 4 larger than 1? Yes. So our new optimized value for this max weight subproblem is 4. We continue making these comparisons down the row and update any new values. Now onto the bug row. We keep the values under its weight since we can't pick the bug up if the max weight is below 4. We make another comparison, this time going back 4, since the beetle's weight is 4. 0 plus the beetle's happy score of 6 is 6, which is larger than our current value of 5. So our new optimized value is 6. Again, we continue making these comparisons and update new values. The rest of the table is filled out in a similar fashion. Now it's time to backtrack to find out what we picked up. Recall that our values only change when we picked up an item. So we work our way backwards from our answer of 10 and go up until it changes. We picked up the bug. Now we move on and back 4 spaces because of its weight and continue until we reach a score of 0. So yeah, dynamic programming is a really useful algorithm. This just gives an idea of what computers do to find answers when we search for questions. For example, if we look up directions, computers can use the traffic, the length of the roads, and also inclines to determine the best route. If you're interested in dynamic programming, you should check out these questions. Thanks for watching.